watch and listen carefully here, guys. So for number 1, we've got dinitrogen trioxide. What do the prefixes tell us? The numbers, right? It's molecular. So di means 2, that's N2. Tri means 3, N2O3, 1 mark. For number 2, we've got calcium chloride, which is an ionic compound. So metal with the charge, non-metal with the charge, then what? Drop and swap. You've got CaCl2, 1 mark. Okay, and there are no half marks here, guys, so don't give them any because I'll just take them away when I enter them. So, okay, don't give them any half marks. Number 3, we've got copper 2 nitride. Again, ionic. What does the 2 tell us about copper? That what? It doesn't tell me that there are 2. It tells me that the charge is 2. Okay, it tells me to use the 2 plus charge and not the other, which is 1. Okay, and it is with nitrogen, which is -3. So when we drop and swap, we get Cu3N2 for our formula, 1 mark. And our last one, magnesium and sulfate, metal and polyatomic ion. So this is definitely an ionic compound. Mg is 2 plus. SO4 is -2. We're trying to get every compound to work out to 0. Does that one already do so? Yes. So MgSO4. You could have gone 2 and 2 and then reduced as well down to 1, right? But in any event, it's MgSO4. If they had the SO4 in brackets, that's fine. Okay. They don't need them on that one, but if they had them, that's also fine. Questions on the first 4? All right. Looking at this next part then. We want to write the names. Sulfur and bromine, what kind of compound? Molecular, because they're both nonmetals. So this is sulfur tribromide, all lowercase. Then it's wrong. Okay, number 6. Well, sorry. Have I told you several times? Make sure you put it in lowercase or it'll be wrong. Yeah, collective gasp. All right, number 6. We've got lithium and oxygen together. Ionic or molecular? Ionic. So we don't need to worry about the 2. It doesn't matter. This is simply lithium oxide. All right, number 7. Iron, which is a metal with nitrogen. Ionic compound. Anything special about this one? Right. Iron is multivalent and has more than one possible charge. How do I know that? Right. If you look at the periodic table, you can clearly see that iron has a 3 and a 2 listed here as its possible charges. Okay, that's what you look for. Always check when you're putting a compound together that it isn't one of these. All right. So this stuff is going to be which iron? If nitrogen is -3, what does iron have to be? +3. So this is iron, Roman numeral 3, nitride. Okay, and the last one, we've got sodium with nitrate. So this is sodium nitrate. All right, now that you've all had the shock, before you give it back to everybody, I will allow the capital letters today, and today only. But let that be a lesson to you, that the next time I will not. Okay? The next time, you will get it wrong if it is capitalized. All right, so what we're going to go over today, guys, is we're going to look at the properties of both ionic and molecular compounds. Okay, so we've talked about how to name them. We're probably not going to spend too much more time on that because that's mostly review from Science 9. Okay, we're going over this because A, it's important, and B, we're going to be doing a lab next week that will involve using the properties we learned about today to identify unknown substances in the lab. All right, so what will happen next week is you'll be given, like let's say a dozen unknown substances, simply identified by letter, like A through J. Okay, and what you're going to have to do is run a series of tests on them to find their properties, and then figure out what each one is. All right, you'll be given a list of the possible identities, and you're going to have to go, well, A is water, B is sodium chloride, C is sugar, or whatever. Right, you'll have to figure out which one is which. Everyone follow where we're going? Okay, so it's important to know, first off, how can I tell an ionic compound from a molecular compound? Okay, what tests will I need to run? Okay, and what are those results going to tell me? Okay, so the key points for today: learn the properties of compounds, acids, bases, ionic, and molecular. The ionic and molecular is the most important part. Okay, acids and bases, that's pretty straightforward. One's below 7, one's above 7. All right. And lastly, understand how these properties can be used to identify a compound. Okay, that, like it says here, is going to be useful next week when you design the procedure for this lab. Okay. All right, so all matter has certain properties. Some are chemical, okay, like how reactive it is, okay, what things does it react with? Does it oxidize? That means like rust if you're iron, or tarnish if you're silver, okay, things like that. And some are physical: color, odor, density, conductivity, magnetism, malleability, okay, all of that kind of stuff. Ductility, all of those are physical properties, sorry. Right? How many people have heard of those before? Okay, hopefully in Science 9 we went over chemical and physical properties. All right, so those properties can be used to distinguish between the types of compounds. Those properties are based on the structure of the atoms. Okay, they're based on how many protons does this atom have in its nucleus. That determines the physical and, to some extent, chemical properties of that material. Yes? All right, so properties of ionic compounds. Ionic compounds are all, without exception, crystalline solids at room temperature. Okay? Does that mean that if you see a crystalline solid at room temperature, it is 100% of the time ionic? It does not. All right? We know that all ionic compounds are crystalline solids at room temperature, but there are some molecular compounds that are also crystalline solids at room temperature. So seeing something as a crystalline solid is a good starting point. It's probably ionic, but we may have to do more tests on it to figure out for sure if it's ionic. All right? What's an example of a molecular compound that would be a crystalline solid? No, that's ionic. Salts are all ionic compounds. You use it all the time. Most of you like it. Sugar, yeah. Okay, sugar is a molecular compound that is a crystalline solid at room temperature. Contains carbon, hydrogen, and oxygen, no metals. Okay. All right. So they have very high melting points. All right, all of them. Now, again, don't mistake solubility, that is dissolving in water, with melting. Are those the same thing? No. Okay, but a lot of people go, oh yeah, I put that in there and it melted. No, it didn't. It dissolved. It's different. Okay, putting an ice cube in water, yes, that melts. All right, but putting salt in water, that's dissolving. It's still salt. It's still sodium and chlorine, and they're still in there. Right, and they've changed the properties of the solution now. When you melt an ice cube in water, did it change the properties of the solution? No, it's still just water. All right, so there's a difference there. Okay, ionic compounds will conduct electricity when they are in solution. So if you put salt into distilled water, it will conduct electricity. Distilled water by itself will not. All right, or will have an exceptionally low conductivity rate. Okay, so any ionic compound, when you put it in water, will conduct electricity. That is probably your most important property or test that you would want to run next week in the lab. Would that test tell you the difference between salt and sugar? Yeah, I mean, salt and sugar visually, if you look really close and you know what you're looking for, you can tell the difference between salt and sugar visually. All right, but if you couldn't tell and you can't taste them, because some of them are very bad for you, okay, you would have to do a conductivity test. All right, the solution of sugar and water will not conduct electricity, because when sugar dissolves in water, it doesn't split into positive and negatively charged particles, where salt does. Right? And that allows it to conduct electricity. All right, so that is probably your most important discerning property that you will use next week. All right, and that happens because we get positive and negative ions. So you can see in this diagram here, all right, when you put salt into water, okay, the water kind of sort of bonds, doesn't really bond, but bonds with the sodium ions that are positively charged, the chlorine atoms that are negatively charged, okay, and then you've got chunks here of sodium chloride that have yet to dissolve. All right. Is there a point if you keep adding salt where it stops dissolving? Anyone remember what that's called? Saturation, right? The saturation point where simply no more can go into solution. That solution is then saturated. All right, so again here, this is a salt crystal under a microscope, right? You can see that they have a very rigid kind of crystalline block-shaped arrangement, and that's because of the charges, right? The way the positives and negatives align when they become a solid, okay, always forces them into a crystalline shape, which is why all ionic compounds are crystalline solids, okay? Because their positive and negative charges force them to orient in a certain way. Okay. All right. Nickel chloride, okay, as an example here, is a crystalline solid, but what do you notice about it? It's green. Yeah. Okay. Certain metals will produce ionic compounds that are certain colors. All right. So if you see a green crystalline solid, it's a nickel-containing salt. All right. It is an ionic compound that it contains nickel. All right. So some ones like that are very easy to identify right off the bat. All right. So if you see a green crystalline solid and one of your compounds is nickel something, that's more than likely it. Would you still want to confirm? Yeah, still dissolve it in water, see if it conducts electricity. That confirms it's ionic, okay, etc., etc. All right, so many ionic compounds produce solutions that are brightly colored. All copper solutions create blue, right? And their salts are also blue, right? So if you see a blue crystalline solid and when you dissolve it in water, the solution turns blue, you've probably got a copper compound there. Okay? Cobalt compounds are pinkish red. Right? Their salts are pinkish red and their solutions are pinkish red. Right? So those ones again are pretty easy to identify. I would make sure that you make a note of those. So cobalt compounds are pink, copper compounds are blue, nickel compounds are green. Right? And that's fine for those ones, but if I give you a sodium containing compound and a magnesium containing compound, they're all white. Okay? Most of the other salts look like salt. They're white. Their crystals might be different, but they're white. Okay. Any questions there? Right. Not very common. Cobalt is fairly rare. So yeah, you're not going to see cobalt salts very often. Yeah. And you wouldn't be able to use a cobalt salt for much because cobalt's a heavy metal. If you were to eat it, it would be very bad for you. It'd be like lead poisoning or anything like that, any heavy metal poisoning. Okay, properties of molecular compounds. So if I'm looking at a molecular compound, things I need to be aware of. They can be a solid, a liquid, or a gas at room temperature. And you're probably thinking, well, that's not very helpful. Well, actually it is. If one of the samples is a liquid, you know it's not any of the ionic compounds, don't you? All right, right off the bat, you know right away, this is not an ionic compound. It's a liquid at room temperature. All right, examples of that could be things like alcohol. All right, alcohol is a liquid at room temperature. All right, certain types of oils, okay, like canola oil, things like that, liquids at room temperature, or have very low melting points, like coconut oil, for example. All right, on a hot day in your house, okay, or on a cold day in your house, or if your house is 20 degrees, coconut oil is a solid. Gets to be about 26 in your house, coconut oil is a liquid. Okay, that's melting point is right in there. You know, it happens to me all the time. It's like, oh, look at this, the coconut oil is melted. Right, it's only 26 degrees in the house. All right. So they have very low melting and very low boiling points. And what we mean by low is like, you know, under 100 degrees. Okay, water boils at 100 degrees. Okay, most of your other ones are going to melt, you know, around that. Sugar might be slightly above that. Okay, it'll melt, you know, at those temperatures. Butter melts low. Okay. Molecular compounds are not usually as soluble. Not usually. Okay, does that mean there aren't some molecular compounds that are soluble in water? Okay, certainly there are. Sugar is soluble in water. Otherwise, we wouldn't be able to sweeten drinks with it. Okay, alcohol soluble in water. right? If you mix alcohol with anything, okay, it just creates a solution, right? You don't see two visible parts like when you pour oil into water, right? That separates, all right? So there are lots of things that are, okay, lots of molecular compounds that are soluble, but they're not typically as soluble. All right. So if you mix two things together, or you mix something together with water next week, and it doesn't dissolve, is it molecular? More than likely it is, okay? But still, you could confirm again by testing the solution for conductivity. If it conducts electricity, it was soluble and it's ionic, okay? It's the degree of solubility. All right, if you put something in water and you're doing a solubility test, is a solubility test a good idea next week? Okay, it is. Let's say you put a chunk of it. You're only going to have a small amount of water here. If you put a chunk of it in there and the whole chunk doesn't dissolve, does that mean it's not soluble? Okay, if the crystals change shape or the solution changes color, is that an indication that it's soluble? Yes. All right, so you have to watch that kind of carefully. All right, you have to look and see, all right, did some properties change? So if, for example, it was distilled water, the pH of distilled water is what? 7. Right, it's neutral. If after you put something in there, it doesn't look like it dissolved, but you test the pH after and it's 14, did it dissolve? Some of it did, all right, because it changed the pH of the solution. So anytime you have a change like that, a physical change like that, you know that there has been some solubility happen, some dissolving has happened. All right, so molecular compounds, not usually soluble, and they will not conduct electricity, okay, because they don't do this, okay? You put an ionic compound into a solution, and it breaks into positive and negative. That's what's required for electricity to flow. Okay, molecular compounds, if they go into solution, remain as a molecule. They do not split up. And so as a result, there are no positives and negatives in the solution to conduct the current. Right? So putting sugar in water will not make it conduct electricity. Questions there? All right. Okay. Now, molecular compounds that are soluble are not going to change the color of the solution. Right? If you just take sugar and put it in water, the solution stays clear. I mean, it might get a little bit cloudy, but it doesn't change to pink. All right? It stays clear or cloudy. Okay, acids. Okay, your strong acids. You have strong acids and you have weak acids. Okay, your strong acids are all ionic compounds, right? And all strong acids contain hydrogen. Okay, so if we're looking at types of acids here, this is a common one. Hydrochloric acid. It's the stuff that's in your stomach. All right, it is a strong acid. Okay? It doesn't eat through your stomach because in your stomach it's fairly diluted and your stomach has a mucus lining, okay, that protects it from the acid. Right? But that's a strong acid. This is also an acid. And so is this. Okay. Which one do you suppose is the strongest? Hydrogen sulfate is it's sulfuric acid. It is very strong, but it isn't the strongest one there. H3N. The thing that makes a substance acidic is how many hydrogen ions it can put into the solution. So the more hydrogen a compound has, an ionic compound has, the more acidic the solution will be. Right? Because as soon as I put this into water, it splits into this. H+, 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 and N, 3-. Okay, so I've put 3 hydrogen ions into that solution and made it much more acidic than, say, adding a similar amount of this, which would only put 1 hydrogen atom into the solution. Okay, everybody follow there? Okay, all right, so hydrogen, the hydrogen ion, H+, right, is the thing that makes substances acidic. So if you have a compound next week that shows up really, really acidic, and one of your possible identities is an ionic compound starting with hydrogen, is it a good bet that it's that one? Yes, those are the things that we need to be aware of when we're trying to figure out what's what. All right. Acidic solutions, strong acids, are ionic compounds, so when you put them in water, the solution will... okay, maybe. What do all ionic compounds do when in solution? Conduct electricity. All right, your acids, your strong acids, will be your best conductors. All right, like on the conductivity meter, it'll go straight up to 10. All right, for most of them, they conduct very well because they dissociate into the H plus and whatever it's attached to very, very quickly. All right, so if you have something that's a strong acid, like when you put the pH paper in there and it shows up like bright red, you know that that's a hydrogen-containing ionic compound. All right, and obviously acids have, acidic solutions have a low pH, less than 7. Okay, acids taste sour or tart. No taste tests next week. Yeah, it's going to taste sour or tart. It'll also be the last thing you ever taste. Okay, I'm sure it tastes very, very tart as it dissolves your tongue. Right? We don't want to have any of that going on. All right, so yeah, no taste tests. All right. Another thing is, acids all typically have a vinegar-like smell. All right. So it's that kind of sharp feeling and smell that you get. You know, if you smell vinegar, it's very distinctive, right? And you kind of get that feeling up here in the top of your nose and in your sinuses. Well, that's because when you inhale vinegar, the vapors contain acetic acid, and that, you know, partially reacts with the inside of your sinuses. All right, it's a weak acid, right? But it gives you that kind of burning sensation. I'm not saying go over top of the unknown solutions and go. Okay, that is also not a good idea. Okay, you will be flat on your back, bleeding profusely from the nose. Okay, if you do that over an strongly acidic solution, I can tell you that because it happened to me once. Okay, I was mixing some acids for a lab, and I sneezed. And right after you sneeze, what do? Okay, wake up and then I get like the blood trails down the side of my cheeks. It was nasty. All right, so yeah, you got to be careful around that stuff. I won't mix it that strong for you guys, obviously, because that'd be a safety issue. But we get it in these glass bottles where it is glacial. That means it's pure. It's not diluted in any way. All right, you drip it on the floor and there's a hole. All right, it's good. It's fun to play with. But okay, yeah. Okay, so you guys won't get it that strong. I will definitely put it in water before you use it. All right, questions on the properties of acids? All right, is a pH test then a good idea next week? Yes, so you'll get pH paper and you'll be able to do a pH test, all right, and that'll tell you for sure the identities of probably one or two of them. You know, you'll have one that's a strong base and one that's a strong acid. The pH thing there that pH test will tell you which one is which. Okay, properties of bases. Okay, bases are ionic compounds, and usually their solutions will conduct electricity. A strong base could be something like this. We talked about this stuff the other day. What's the name of that compound? Sodium hydroxide. Right? Sodium hydroxide is the active ingredient in oven cleaner. Right? Strong bases can do just as much damage to human tissue as a strong acid can. Okay, strong base, strong acid, equally what we would use the term is caustic. Okay, caustic means can create a chemical burn. All right. If you were to get that stuff on your skin, you would need to rinse it underneath the sink for 5-6 minutes, okay, at a time. All right, it would give you pretty bad chemical burns. All right. Similarly, this is a strong base. This is a fairly strong base. All right. This is also strong. What do they all have in common? They all have hydroxide on them. Hydroxide is the counterpart to hydrogen. Hydrogen makes things acidic. Hydroxide typically makes things strongly basic. Right? So all of these are strong bases, right? And they all contain the hydroxide ion. So if you have, let's say, next week a solution, when you put the pH paper in, it turns like bluish black. Right? It's got a pH of 14. You look on your possible identities and you see something that ends in OH. All right, that's an ionic compound. Is that probably it? Yes. Now, something to be aware of. You could run into something like this, C2H5OH. All right, is that a strong base? Okay, it's not, because it's not what kind of compound? It's not ionic. Okay, is there a metal listed first on that compound? No. Okay. Here's one that's tricky. You'll sometimes see this, CH3COOH. What's that stuff? That's vinegar. It's acetic acid. Okay, why is it called acetic acid? This ion is on your table of polyatomic ions. On yours, it's written like this, CH3CO2. Okay, and it's -1 charge. It's acetate. This is acetic acid. When this breaks up, it breaks up into this and that. Okay, gives away a hydrogen. That makes it acidic. Yeah, molecular. You can have weak acids that are molecular. Yeah, your strongest acids and strongest bases will be ionic compounds. Strong acids will be ionic compounds starting with hydrogen. Strong bases will be ionic compounds ending in hydroxide. Okay, this is not a hydroxide containing compound. Neither is the C2H5OH, right? This is a molecular compound because it starts with a nonmetal. All right, so things like that we've got to be aware of, right? All molecular compounds start with a nonmetal. Okay, so basic solutions have a pH higher than 7, and again, next week when I give you your unknowns and you're testing them, you're going to have one that's a super strong base, one that's a super strong acid, and everything else will be kind of in the middle. Okay. Now, basic things typically are bitter. Typically. Should you be tasting anything? Okay, I'm sure oven cleaner tastes very, very bitter. Okay, but again, it'd be the last thing you ever tasted. All right, so we don't want to be doing any of that. All right, but soap, does it taste bitter? Okay, yeah, well, it's basic. You make soap by taking fat and lye and putting them together. All right, at a basic level, that's soap. Okay, fat and lye. You put it together and it makes soap. Okay, that's why it lathers up. But lye is very, very basic. Okay, it's essentially sodium hydroxide. Yes. Yeah. Okay. All right. All right. So that's it. That's all you need to know about the properties of the compounds. All right. What I want to go over now, okay, is some stuff to do with how you assemble your proper lab report. Okay, so any more questions on properties there? Okay, did you make notes there where I said this would be important for identifying stuff? Okay, if you didn't, you'll need to watch this podcast again and make sure you do that, because when you're doing your lab report for the lab we do next week, you're going to have to identify those compounds. I'm not going to tell you what they are.